Recall the definition of equivalent matrices. We say that two matrices are equivalent to each other if you can obtain one from the other one using a sequence of elementary row operations, right? So let us go back to previous slide, identifying the elementary row operations that we did to obtain the second matrix from the first matrix. The second matrix can be obtained from the first matrix by interchanging row 1 and row 2, then add 3 times the new row 1 to row 3. We say that a row is called a zero row if all entries on that row are equal to 0. For example, take a look at this one. 0, 0, 0, every entry is equal to 0. Let us move on to the definition of row-reduced matrix. A matrix like R is called in row-reduced form if the first non-zero entry that you see on that row is equal to 1. 2, each column of R that contains the leading non-zero entry of some row has all its other entries equal to 0. Now we're going to introduce row-reduced echelon matrix. We say that a matrix is in row-reduced echelon form if, first of all, these two conditions are met. Matrix is already written in row-reduced form. Then every row with 0 entries land on the bottom of the matrix. And finally, if rows 1, 2, 3 are the non-zero rows of matrix R, and if the leading non-zero entry of row I occurs in column Ki, then K1 is less than K2, less than K3, less than Kr. Two obvious examples for you are identity matrix and also zero matrix. For identity matrix, the very first entry is 1, and all entries below 1 are equal to 0. On the second row, the non-zero entry is 1, and all entries above and below 1 are 0. On the third row, the non-zero entry is 1, and as you can see, every entry above 1 are equal to 0. So on the exam, if I ask you to give me two obvious matrices written in row-reduced echelon form, you can give me these two examples. More examples for you. Here, for this matrix, the leading element, the leading entry is 1, and everything below 1 are equal to 0. On the second row, it starts with 1, and every entry above 1 and below 1 are 0. And down here you have a 0 row, which lands on the last row or bottom of the matrix. Note that the first condition in the definition implies that a matrix in echelon form will have 0 falling out the column below each of the leading term. For a matrix in echelon form, the pivot positions are those that contain a leading term. So when you hear pivot position, it means that you are working with non-zero leading terms. Two examples of matrices that are not in row-reduced echelon form. Take a look at this guy. So first of all, 0, 0, 0 lands on the first row, but note that also here, down here, the starting or the leading term has a leading coefficient 2, which should be 1. Another example for you. Take a look. Here you have the last row, 0, 0, 1. Okay, we don't have any issue with 1. But above 1, this guy should be 0, not 2.